Thank you to Radio Code for supporting PBS. They say fusion is 50 years away, and they've been saying that for 50 years, but if so, why are billions suddenly being pumped into fusion startups? Well, to train LLMs, but there's a reason that the technobrats are bullish on fusion in particular. The fact is the technological challenges have been chipped away at and in many cases solved over the past decades, and there's really no one deal-breaker difficulty remaining. One of the final challenges is deciding on the physical vessel to contain our mini artificial stars, and we have some pretty sci-fi options that are nearly ready to music. Go. Hey everyone, quick update before we start. We've observed that the YouTube algorithm isn't promoting our episodes within the community as much, and so we're conducting an experiment over the next few episodes. We'll test where increasing likes and comments impacts sharing. If you'd like to be a data point in this experiment, hit like and or leave a comment, and if you're new and enjoying this, subscribe and please press the bell. We'll analyze the results and report back after a few episodes. Solar power is the ultimate in clean energy, and it's delicious when you can get it, which isn't everywhere all the time. But solar power is just fusion power that's happening far away. Slam hydrogen nucleo together into helium, and a bit of the original mass is converted into energy in the core of the sun. That energy mostly radiates into empty space with a minuscule fraction hitting the Earth and powering nearly all of life. A minus fraction hits our solar panels, and only in well sunny places. And times there's a limit to how far we can scale solar energy collection until we build our Dyson sphere. But why build a cage around the star if you can instead build a star inside a cage? What if we can run min suns right here on the surface of the Earth? That's the goal of the artificial fusion reactor today. I want to talk about a specific aspect of fusion, and that's how to confine hydrogen fusion in a way that leads to a net energy output. I want to talk about how to bottle a star. I'm going to reference here a lot. That's the European fusion experiment, and I'll refer to it because it's the largest and arguably the most advanced, and is projected to achieve first plasma this year. I do want to emphasize though that there's a lot of exciting stuff in recent years from smaller efforts. Both national programs and increasingly private endeavors will come back to some of the more speculative ADV answers another time. Let's start by taking whatever lessons we can from the sun. Our home star sustains a steady rated fusion for billions of years because it confines its nuclear inferno by crushing it under the weight of 100,000 Earth's single protons. Hydrogen nuclei are fused in a series of steps to produce helium-4 plus a lot of energy. The sun's proton-proton chain runs at something like 100 million Earth atmospheres of pressure and over 50 million Kelvin temperature, generating the equivalent of 20 million times the entire world's nuclear arsenal in energy every second. So the sun both crams photons together and gets them moving really fast. In order to get them to stick, we need to do the same. We need to both compress and heat our nuclei, and the resulting fusion needs to output more energy than we used to reach that state. One big efficiency upgrade is to focus on the most energy-rich fusion reactions rather than going all the way to helium from single protons like the sun does. We can fuse heavy hydrogen isotopes like dium and tritium. Now the sun can achieve net energy gains starting with protons because of the incredible densities it reaches. We can never achieve those densities, so even with heavy isotope fusion we have to compensate with a lot higher temperatures. In fact, something like 100 times the temperature of the core of the sun. There is no material in the universe that wouldn't be instantly vaporized at the temperatures needed for fusion. So how are we supposed to even contain our fusion reaction, let alone crush it to the needed pressures? Well, there are two broad approaches: inertial confinement and magnetic confinement. Inertial confinement attempts to slam nuclei together with some sort of shock. In 2022 the national facility achieved net energy output for the first time by forcing fuel together with lasers, but it's not the first inertial confinement approach to succeed. The hydrogen bomb is a type of inertial confinement where the thing slamming nuclei together is a fission bomb, an old-school atomic explosion. The latter is rather uncontrolled and so not suitable for sustained energy production, but even controlled inertial ferment approaches have the issue of rather bursty energy output, and so are generally not thought to be the most likely option for our first-generation commercial fusion reactors. Those are more likely to be magnetic confinement reactors. The hydrogen in a reactor is so hot that positively charged nuclei are stripped of their negatively charged electrons, making a plasma of electrically charged particles that can be manipulated by magnetic fields. These fields are created by powerful electromagnets made from superconductors, and those superconductors have to be cooled to near absolute zero, so you have the center of a star-hot plasma mere meters away from matter that's colder than intergalactic space. So to bottle our star we have to create the largest temperature gradient in the known universe, which is I guess something to be proud of. All on its own. Magnetic confinement reactors work by squeezing the plasma so it flows around the torus, and then compressing the torus with a magn field and heating it by blasting it with energy via particle beams or EM waves until fusion is achieved. This has to be done cleverly because if you just run plasma in a circle it leads to various instabilities that are fatal for your plasma and perhaps for your reactor. The leading solutions for stable TDAL plasma confinement are the TOC and the accelerator. The details of the differences aren't too important here, but TOCs are more widely used, for example by ear, so I'll cover these just briefly. TUMACs use three systems of magnets. The first system is the pital system, which is the main containment system and gives the plasma the donut shape. The next system is the poloidal system, which helps shape and position the plasma near the inner wall. This is to help compress the plasma for more reactions to occur. Lastly, the central solenoid drives the direction of the plasma, spitting the plasma in a circle. In contrast, accelerators combine all three magnetic systems into one using a 3D design, making them significantly more complicated. To some extent, the magnetic field is a relatively solved problem. There are no doubt refinements to be made in the form of the field and definitely in the generation of the field with new superconductor technology. That's something we can come back to another time. Currently, one of the biggest engineering and research challenges in fusion is how to build the actual physical containment chamber for that field and the plasma it holds. How do we build a wall that can hold a mini-sun? The magnetic field certainly help by creating what's called a pedestal region where the plasma is cooler and sparer relative to the middle where the fusion reactions are happening. This helps create a small buffer between the fusion plasma and the wall. So the material doesn't literally have to withstand contact with millions Kelvin plasmas, but it still has to do a lot. That wall is the first point of contact between the plasma and the outside world, and we call the plasma-facing surface the first wall. While the magnetic field keeps the highest temperature parts of the plasma out of direct contact with the wall, a lot of energetic particles do reach it, and the wall needs to withstand that. It then needs to take the heat generator by this incoming radiation and transport it to somewhere useful to actually generate power finally. As if all this wasn't enough, the chamber wall needs to create new fuel for fusion. Let's look at these one by one. Within the coiled ribbon of the millions of Kelvin plasma, heavy hydrogen nuclei collide and release energetic gamma rays and very fast-moving neutrons and helium nuclei. Those gamma rays and helium nuclei help keep the plasma hot, so hot it radiates X-rays. This thermal radiation bakes the outer wall of the chamber, and the wall has to very quickly conduct this heat to the cooling system, or be at risk of melting. Even more energy is carried by the neutrons. These neutral particles are not affected by the magnetic field, and so they fly straight out of the plasma. They deposit kinetic energy into the wall, and this is the main source of heat energy from fusion. Some neutrons hit nuclei in the wall, potentially creating unstable isotopes, and some helium and hydrogen nuclei also end up with enough energy to escape the magnetic field and reach the first wall. Some of these are tritium nuclei, which are also highly unstable. As a result of the neutron and tritium bombardment, the wall becomes more radioactive over time. These impacts also erode the wall, with the wall's own nuclei getting smacked from the surface into the plasma chamber in an effect called sputtering. This degrades the shielding over time, and also contaminates the plasma. Finally, an imperfect wall structure can lead to runaway instability abilities in the plasma called edge localization modes. These can result in localized failures of the magnetic confinement and to large amounts of energy being dumped into the wall, which is not good for the wall. This can also trigger larger magneto-hydrodynamic instabilities in the plasma, causing the plasma to shed a lot of energy and potentially kill the fusion reaction. Assuming our wall can survive the above, the heat generated within the wall will be carried away by some working fluid. Water is a popular choice, but also molten salts and even lithium, the working fluid. Both cools the wall and heats the fluid to the point that it can turn a generator. Okay, so we've just generated electricity, nice, but even if we got more power out than we used to create our plasma, this process is not sustainable. The diam part of the fuel is enormously abundant. There are 33 g per cubic meter of seawater, which means it's basically limitless, but the tritium is not abundant. It has a half-life of 12 years and so is almost non-existent. Naturally, the reactor has to make its own tritium. That's not super complicated. Hit a lithium nucleus with a neutron and it'll split into two nuclei, so the trick is to place a layer of lithium behind the first wall. That wall will slow neutrons from the fusion reaction, extracting some of their energy, and the neutrons will then hit the lithium and breed tritium. Obviously the lithium has to be replaced, but fortunately lithium is moderately abundant with thousands of years worth in the ground and millions of years worth in the ocean. One major issue with this is that the fusion reaction doesn't produce enough neutrons to breed a sustainable amount of tritium. To deal with this, a neutron multiplier is needed. This is a layer of material that amplifies the neutron flux. One neutron goes in and two come out to feed the tritium breeder. That way the fusion reaction replaces the tritium it uses. So now that we know all the miracles that the reactor wall has to pull off, let's look at options for materials. The most traditional pick for a fusion reactor first wall is the metal tungsten. It's metal, so it's structurally strong, and it has the highest melting temperature of all metals, so it can stay solid under heavy bombardment. It's also less inclined to hold on to as many of the radioactive tritium as other materials, and very importantly, it has a low sputtering rate. Fewer tungsten nuclei ejected into the plasma. However, it does have a major weakness with regard sputtering, in that those tungsten atoms that do join the plasma have a pretty unfortunate effect. Tungsten has 74 protons in the nucleus compared to hydrogen's 1 proton. That means tungsten's electrons are much more strongly bound, so while the plasma's hydrogen is fully ionized, liberated of electrons, the tungsten atom will retain 20 or 30 electrons even when inside the plasma. So now when a tungsten atom bumps into another particle in the plasma, some of the energy of the collision goes into exciting one of those electrons. That electron then drops back to a de-excited state, emitting a photon in the process, and that photon then escapes the plasma, taking that energy with it. The larger the atomic number of the atom, the more electrons it can retain in the plasma, and also the smaller the energy gap between electron levels. That means more opportunities to absorb energy from the plasma and radiate it away. This effect is called line emission cooling, and it's a great way to lose a lot of energy from your plasma very quickly. Even a little bit of a heavy element like tungsten in the plasma can make it very difficult to keep it hot enough to sustain fusion. Tungsten has major advantages, but the issue with pollution of the plasma was enough to convince the EAR team to try something different, at least to start with. In fact, they plan to go in the opposite direction to tungsten in terms of location on the periodic table by using beryllium for the plasma-facing wall. Barium is the fourth element on the periodic table, so even though it will end up polluting the plasma, those contaminants tend to be completely ionized. There are very few electrons left to radiate away the plasma's heat. In fact, beryllium actually removes balance. It can capture oxygen impurities, which themselves are released from oxidized metals in the vessel wall. When the machine is running, oxygen in the plasma can cause the plasma to cool just like tungsten. Barium has other major benefits. It has extremely high thermal conductivity, allowing it to quickly transfer heat from the front plasma-facing surface to the back surface with the cooling systems. And one of the most compelling benefits of barium is that it acts as a neutron multiplier, doubling the neutrons available for tritium breeding. So what's the downside? Well, barium does have a much higher sputtering rate than tungsten, and even though the ejected impurities don't harm the plasma as much, this does mean the barium surface erodes much more quickly than tungsten, and that means the wall needs to be replaced more often. Also, fluctuations in the plasma will induce electrical currents in the barium wall, and those currents experience massive forces in the ST magnetic field. This can damage the wall and even cause it to fail while the reactor is running. And a huge disadvantage of barium is that its extremely toxic erosion of the wall fills the reaction chamber with barium dust, which cannot under any circumstances be allowed to get out of the reactor if you want to keep your nuclear engineers operational. Finally, beryl is super rare. ITER would need 12 tons of the stuff for the first wall. EAR had originally planned a barium first wall, but just in 2023 they decided that the hassles outweighed the benefits and shifted their plan back to good old tungsten. This is a pretty safe choice for EAR as an experimental facility, but for commercial fusion some kind of neutron multiplier feeding the EM breeder is needed, and ITER is currently testing various options, so we still have the problem of tungsten polluting the plasma. There are other options for the plasma-facing surface though. Boron is currently getting the most attention from the EAR crew since it's the next lightest element after beryllium. The idea is to build a tungsten wall and then sprinkle a little bit of boron powder into the reactor while it's running. This should then evaporate and coat the wall, reducing the amount of tongue that cooks off into the plasma. Boron does have the icky side effect of retaining tritium, which means the inner wall could become dangerously radioactive over time. Meanwhile, going in the other direction on the periodic table from barium, we get lithium, which, if you remember, we were using to breed tritium behind the first wall. At first glance, lithium seems a non-starter for the plasma-facing wall because lithium metal has a melting point of 82 degrees Celsius, but who says the first wall really has to be solid? There's this idea to coat the reactor chamber in a layer of liquid lithium, which has many advantages. You can't really damage liquid structurally. Seriously, go try to hit a lake with a hammer and see what happens. Lithium nuclei would end up in the plasma instead of the tungsten behind it, but this is actually good for the plasma. Getting up to fusion temperature requires physicists to add large amounts of energy both with EM fields and with neutral beam injectors. Experiments like the lithium toad experiment beta at the Princeton Plasma Physics Lab suggests that a little bit of lithium in the plasma may help the plasma get to the temperature more easily. Finally, the lithium can even double as a coolant and the tritium breeder if it moved through and behind the tungsten wall. And as I said, ITER is supposed to produce its first plasma this year, but is projected to achieve its first fusion reaction in 2035, smashing two DUMs together to produce helium-3. Now its first commercial-grade diam-tritium fusion reaction is slated for 2039. If all that works, then I guess we build a lot of them, but it's also possible that one of the many smaller enterprises will beat EAR. They certainly talk a big game, with some projecting first fusion in the next few years, but that's a story for another episode. Personally, I don't care who wins, I just want my infinite free energy so I can train a godlike LLM to take over writing spacetime. Thank you to Radio Code for supporting PBS. If you're looking for a new science-based hobby, Radio Code is a gadget that's made for all natural science enthusiasts. Radio Code is a portable radiation detector that start fast. Now you can not only quickly locate the source of radiation, but also identify which isotopes are present, such as cesium-137, thorium-232, radium-226, and many others. The multifunctional app included with the device works on iOS or Android and makes it easier to explore and research by allowing you to record radioactive GPS tracks on maps, keep a measurement log, analyze spectra, create charts, and build spectrograms. You can learn more about Radio Code by following the link in the description and the pinned comment below. Use promo code PBS to get an exclusive 10% discount. Hey everyone, before we go, we wanted to let you know we're celebrating the 50th anniversary of the Space Shuttle patent with some limited edition merch in the merch store. There's multicolored hoodies and t-shirts featuring the original patent, the first ever Spacetime notebook, as well as a re-release of the multifunctional Spacetime pen in new colors. You can check it out at pbsbtime.com shop. There's a link in the music description. Music